and today I am starting the module 5, that is material science. Here in this module, we'll understand the electrical properties of the materials like the conductors, metals. So to start with the metals, you know that the metals are the good conductors of electricity, isn't it? Metals are good conductors of electrical conductors. They are also good thermal conductors. These are the some of the properties I have listed here. They obey Ohm's law. You know that V is equal to IR, where V is the voltage, I is the current, R is the resistance. What is Ohm's law? If for any conductor carrying current between 2 points, the voltage developed is directly proportional to the current. V is equal to V proportional to I. And this proportionality constant is called as resistance. V is equal to IR. You know that Ohm's law. So metals they satisfy the Ohm's law. They satisfy the Ohm's law very well. And the other properties of they you know that the resistance is directly proportional to the temperature in case of metals. The resistivity of the metals varies with temperature. What is resistivity? It is a measure of resistance with per unit length of the material for a uniform cross sectional area of a conductor. That is resistivity. And you know that certain metals, when brought nearer to 0 Kelvin, that is minus 273, they loses its resistance completely. They lose its resistivity completely. The resistance goes to 0, and conductivity goes to enormous values. It's infinity. Conductivity shoots to infinity. This property is called the superconductivity. So certain metals do exhibit superconducting properties. And when you bring again some metals, these conductors, into the field of magnetic field, when you brought into the magnetic field, they offer resistance. They show some resistivity properties. They exhibit resistivity in the presence of magnetic fields also. That is called the magnetoresistance. The ratio of thermal to electrical conductivity is, it is directly proportional to the absolute temperature. That is as called the Weidmann-Franz law. So these are some of the lists of the properties of the metals. And here given the table of resistivity and conductivities of some materials. The first three material are the metals here. They are the silver, copper, aluminum. The fourth one is carbon, germanium, silicon. These two are the semiconductors. You know that. Polyethylene, last one, is an insulator. Look at the resistivity. The values of resistivity is for mercury. Silver is 1.47 10 to minus 8. The order of 10 to minus 8. Again for copper, it's order minus 8, 10 to the minus 8. So, and the third column represents the conductivity. The resistivity is order minus 8, very small. The conductivity is the order of 10 to the power of 6. So, for metals, resistivity is small, very small, minus 8 order. The conductivity is order of 10 to the power of 6. Carbon is again little, but it's order of 10 to the power of 6 conductivity wise. And look at germanium and silicon. You know that they are the semiconductors. Their conducting properties lies between that of an insulator and as well as a conductor. So look at its order is around somewhere 10 to minus 4, some plus value to 10 to minus 4. When you look at the conductivity of insulator, the last one is 10 to minus 13 to minus 15. So this is a brief view of the resistance and conductivity. The resistance conductivities are inversely proportional, you know that. Now, in this chapter, we are trying to understand the electrical properties, electrical conductivity of the metals, particularly the conductors. So, to explain this electrical conductivity, in the year 1900, in the year 1900, Drude and Lorentz proposed a theory to explain the conductivity of metals. This is the first theory of metals. They explained the electrical conductivity based on certain assumptions. I have listed these assumptions in the coming slides. But now I explain the electrical conductivity. They explained the electrical conductivity considering a conductor, for example, copper, whose valency is 1, and its atomic number it is 29. Z is 29. There it has got 29 electrons. They have been allotted to various energy levels. You know that according to Aufbau's principle. If you remember the electrical configuration of copper, that is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, and 4s1. So the 4s1 is the outermost shell, shell, and s is the orbital, suborbital, subshell, and it has got the one electron, 4s1. So all 28 electrons are inside, and the 4s is the outermost shell, and s is the 4s shell is the outermost shell. 4s, is the valence electron. You know that S shell can have maximum of 2 electrons. So this is half filled. So it is partially filled. So it is 4s1. So it is 50% filled. This 4s electron is responsible for the electrical conductivity. See, in any chemical reaction or electrical conductivity, the valence electrons, the outermost shell electrons are responsible for the properties. So this 4s1 is responsible for the electrical conductivity. These valence electrons are also called here the free electrons or the conduction electrons. These valence electrons are very tight, loosely bound to the atom. Okay, all of the inner shell electrons are tightly bound; they are firmly fixed to the shells, and only the valence electrons it is lightly bound to the atom. Therefore, it can be easily released or it can be easily removed with small potential, or there may be a small even with thermal energy, the valence electrons gets released. So with it requires only small amount of energy, either electrical or thermal, so that it can be easily removed. Here, this Drude and Lorentz, in order to explain this electron theory, electrical conductivity, they assume that the electrons here in the substance are solid as electron gas. They treated the see once if you apply a small potential difference or even because of the thermal energy, the electrons are easily released. They got you got the CF electrons. They are simply moving at random within the solid. They have been right now. They are moving in all directions, just like imagine just like the gas molecules in a container in a vessel. So they have treated this movement of electrons just like the gas molecules and called this as electron gas, and applied the kinetic theory of gases to explain the electrical conductivity. So look at the diagram here. The first one, the plus, and there is an orange dot. The orange dot refers to the free electrons. The plus is the nucleus along with the inertial electrons. If you take copper, all that nucleus along with the 28 electrons is here plus, and the orange dot refers to the free electron. Copper gives only one free electron, conduction electron. So these the electrons, they are keep moving in all directions. Imagine this: you got this solid under the absence of the electric field. So it not applied right now any electrical field, no external electric field. I told you that under the presence of the thermal energy is sufficient, because you need to have a material at some particular temperature. So it is existing at some temperature. Imagine that the electrons, the free electrons have been released. and the released electrons now they are bound to the atom. They can easily freely move in a system. Look at the second diagram. That is the electrons have been moving at different directions. So all directions, all possible directions, they keep moving, and they're having certain velocity, isn't it? These moving electrons they got a certain velocity. They are moving in all directions. If you take the vector sum of all these velocities, it will become zero. If you take the vector sum of all these velocities, it will become zero. For example, the electron is moving in north direction. Imagine the other electron is moves in south direction. If you take these two, the vector sum is zero. Like that, if you take all these electrons, movement of electrons in a crystal, their velocity, net average velocity is zero under the absence of the external field. Therefore, you don't feel the electrical conductivity under the absence of electric field because of the net average velocity is zero. Here, that what I have explained so far, just a brief summary of this in this slide. When an atom loses valence electron, it becomes positive ion, isn't it? When electron is lost, valence electron is liberated, released from an atom, the atom loses one electron, therefore it becomes positive ion. These ions, see here, we have considered the copper is a crystal. Copper, the metals are crystals. So in a crystal, the atoms have been arranged at regular intervals. They have been, the atoms have been fixed to regular points. There is a regular arrangement of atoms in a metal. So in a crystal, the electron, in an atom, there is a regular distribution of atoms that is there. And since this regular arrangement of atoms, the released electrons, they have been moving in all possible directions, isn't it? The electrons, they move in all possible directions. The ions, they have fixed the lattice. They have been vibrating about their mean positions. Here, the ions, they get thermal energy from outside. They are not simply sleeping. They have been vibrating about their mean position. This causes the elastic waves in the crystal. The vibrations of an electron, a vibration, the fixed lattice ions, they cause the elastic waves in the crystal. Now there is, imagine there is an electron, free electron that is moving. When such a free electron comes nearer to such the ion, vibrating ion, it gets scattered. It changes its direction of propagation, isn't it? When an electron comes near to this vibrating, it changes its the direction of propagation. It changes its direction of propagation, initial direction of propagation. And again it meets another positive vibrating ion. Again it gets another reflection. And so like that, wherever it goes nearer to a positive ion, it is getting another changing directions and so on. So now this, there is complete, there is a series of reflections that have been taking place here. And imagine a situation of a football match, where in the football match, how do you see that a football, there is football during the play. This football is moving at the different players, moving at the different players, because the aim of this match is not to see that one side wants to have a goal, other side wants to avoid the goal, isn't it? So just like that here, the electron feels as if it is a football here, and it is kept on moving. It is between the lattices. So it undergoes n number of these movements, reflections. So and finally it arrives at the end. So now this is the situation of an electron under the absence of field. Therefore, since the electron is being seen getting n number of scatterings, reflections, when you look at its velocities, the average net velocity of the electron will be zero. Hence, the overall the system of atoms here, see that there is no conductivity. In the absence of the field, the net velocity of the electrons is random, and as a result, there is no net transfer of charges. Hence, material remains in the electrically neutral condition. Isn't it? Now, the field is applied. So far, what you understood under the absence of field, the net velocity of the electrons is zero. Since the velocity is zero, you cannot expect the electron to move. Therefore, the conductivity is zero. Now you apply the field, sufficient field, you apply a sufficient field. So now, though there is initially the randomness in the motion of the electron there, but because of the external field, there will be overall shift in the direction of the movement of the electrons against the field direction. Because of the external field is acting on these electrons, initially there are some random motions of the electrons, but overall as the field is increased, all this randomness goes, and there creates a situation where keeps moving in one start moving in one particular direction. So the net displacement of electrons, now it becomes a constant value. So net displacement of in the velocity of the electrons, now it gains a positive value. And if you maintain a constant potential outside, you expect the electrons to gain a constant velocity. This velocity of the electron in the uniformly or a constantly applied field is called the drift velocity. So now the electrons gains a positive value for its velocity, for its value for its movement. So it is not zero under the application of external field. They will gain a positive value. This positive value of velocity in the uniformly applied field that is gained by the average electrons is called the drift velocity. And as you see that the electrons they move, then they will not move in straight lines because of the lattice ions, as they will keep moving zigzag they undergo a zigzag motion and finally arrives at the other side. There will be overall transfer of electrons from one side to the other that takes place. This is actually the conductivity. When electrons move from one side to the other side, overall drifting of electrons is taking place from one side to the other side. It represents the electrical conductivity. So they don't go in straight lines because of the lattice cores in between. They undergo even now there are many reflections, scatterings, but ultimately reaches the other end because of the external potential applied. This is called the conductivity. This is how we can explain the conductivity in electrical in metals. See now, as soon as as it travers, it is going to get scatterings from the this lattice cores. So now here this lattice cores they are just like they are opposing the movements of the electrons. The opposition felt by the electrons because of the lattice vibrations is called the resistance. The overall opposition felt by the electrons for the movement for its movement under the lattice vibrations is called the resistance of the material. That's how we can explain the electric conductivity in case of a conductor. So under such condition, the expression for electrical conductivity, the symbol sigma is the notation used for conductivity. The electrical conductivity sigma is given by this expression. Sigma is equal to n e square tau. It is tau by m, where tau represents the collision time, n is the free charge carrier concentration, and m is the mass of the electron. And here tau is said to be the collision time. It represents the average time taken between any two successive collisions of the electron with the lattice. How to define this collision time tau? It is the average time taken between any two successive collisions of the electron in the lattice.